Hello and thank you for tuning in to my talk. My name is Hadley Black. I'm from UCLA, and this is a joint work with Deeparnab Chakrabarty from Dartmouth and Seshadhri from UC Santa Cruz. So the problem that we study is known as monotonicity testing, and this is one of the central problems in property testing that was proposed and originally studied by Goldreich, Goldwasser, Lehman, Rahn, and Samranitsky. And the setup is as follows. So we consider Boolean valued functions over the hypergrid n to the d. And such a function is monotone if it's non-decreasing with respect to the coordinate-wise partial order over n to the d. And the distance to monotonicity of a function, denoted by epsilon of f, is simply the minimum Hamming distance of f to any monotone function, and then we normalize by n to the d. So for instance, here is a monotone function, and here's another function whose distance to monotonicity is 1/3, because there are 9 points in the domain, and we can easily make it monotone by changing these 3 zeros to 1s. So the problem asks us to design a randomized algorithm called the tester, which is given query access to some input function f and some distance parameter epsilon, and should distinguish with high probability between the case when f is monotone and f is far from any monotone function. So formally, the distance to monotonicity is greater than epsilon. And the query model that we consider is quite simple. You can request the value of the function at any point in the domain, and specifically, we consider non-adaptive testers, meaning that the tester specifies all of the points it's going to query up front before receiving back any of the answers. And the testers we consider are one-sided, meaning that if the function is monotone, then the tester is guaranteed to accept. So as a consequence, if the tester is going to reject a function, it must have seen a proof that it's not monotone. So it must have seen a pair of points x and y, which violate monotonicity. So the essence of the problem is really how many queries do we need in order to find such a pair under the assumption that f is far from any monotone function. So naturally, the most well-studied setting for this problem is the case when n equals 2. So this corresponds to the hypercube domain. And there's been a long line of work studying this problem going back to the original paper, which achieved an O of D query tester. So Chakrabarty and Seshadhri in 2014 were the first to achieve sublinear in D. And the key insight that allowed this was that there's a connection with isoperimetric inequalities on the hypercube, and I will talk more about this shortly. And Koopmanzer and Safra, in a seminal paper in 2015, were able to push this observation further and achieve a square root D query tester, which turns out to be optimal among all non-adaptive testers. So Chen, Waingarten, and Xi proved this lower bound, and they also proved a D to the 1/3 lower bound for adaptive testers. So now turning to the case of general N, so for general hypergrids, as of 2014, the best known tester was still essentially linear in D. And somewhat recently, we were able to get D to the 5/6 in 2 papers from 2018 and 2020. And now in this paper, we get a tester which makes n square root D queries. So this is optimal in D, but there is this sort of suboptimal dependence on n. But I'll point out that this result wasn't even known for n equals 3 prior to our work. So we're the first to achieve this optimal dependence on D, even for the case of n equals 3. And to do so, we extend an isoperimetric theorem, which was proven by Koopmanzer and Safra, to all values of n. And the old proofs are highly specialized to the case of n equals 2, so we require a lot of new ideas even to go to n equals 3. And I'll mention a recent parallel work, which was done by Braverman, Coate, Kindler, and Minzer, and it was published in ITCS this year, which achieved a very similar result, but with completely different techniques. But there's an interesting similarity, which I'll point out later on. So I'd like to first talk about how monotonicity testing and isoperimetry are related in the case of n equals 2, so for the hypercube. So overall, the strategy of designing a monotonicity tester is to try to find 2 points which form a violation, right? And if you can find such a pair, then you can reject, and if not, then you'll accept. So one way to think of this is you want to find a pair of comparable points which straddle the upper boundary of the set where the function is a 1. So perhaps the most natural way to do this is to simply sample uniform random edges in the hypercube and check if they form a violation. So this is the test that was actually considered in this original paper I mentioned. And so you're going to sample edges, and as soon as you see a pair which straddles the upper boundary, then you will reject. So what is the probability that this test finds a violation? So to think about this, we'll introduce a little notation. So the negative influence of a function at a point x is simply the number of violating edges which are incident to x. And the negative influence of f is simply the expectation of this value over all points. And so what they proved in this original paper is that the negative influence is always omega of the distance to monotonicity. So in other words, the number of violated edges is always epsilon of f times 2 to the d, at least this. And since the total number of edges in the hypercube is d times 2 to the d, this means that a random edge will be a violation with probability epsilon over d, and so repeating this d over epsilon times yields a tester. Now what's really cool is that if you replace the negative influence by the total influence, and you replace the distance to monotonicity by the variance of f, you recover the edge expansion bound due to Poincare. So you can think of this inequality on the left as a directed version of Poincare's inequality. So now the question is this analysis of the edge tester optimal? So in other words, is this inequality tight? And it's not hard to see that the answer is yes. We can simply look at an anti-dictator function, which assigns a value of 1 to the points where the first bit is 0, and a value of 0 to the points where the first bit is 1. And you can see that the distance to monotonicity and the negative influence are both exactly a half. So this inequality is tight. And so as a consequence, in order to beat O of D queries, we need something other than the edge tester. And so one natural thing to consider is to sample pairs of points at distance more than 1, right? So a random edge is like a pair of points which differ by 1 bit. So now we can also consider sampling pairs of points which differ by more than 1 bit. So this was considered originally by Chakrabarty and Seshadhri, and they called this the path tester. So we sample x uniformly at random, and we obtain y by a directed random walk of length roughly square root d from x. So what is the probability that this detects a violation for the anti-dictator function? Well, all we need is for x to have its first bit be 0, right? So for x to be in the left side of the function, and for one of these square root d steps to flip the first bit from a 0 to a 1. So this shows that this test will succeed with probability 1 over square root d for the anti-dictator function. So this is a great improvement over the 1 over d bound for the edge tester. And so why square root d? Well, if you think about it, you can't walk farther than square root d simply because the standard deviation of the binomial distribution is square root d. And so if you walk farther than this, you end up in one of the caps of the hypercube. And we can always modify whatever function we're looking at to have a 0 in the lower cap and 1s in the upper cap. So if you walk farther than square root d, you won't discover anything interesting. Okay, so at a high level, why does this test work in this for this example? So at an intuitive level, this is because the edge violations, even though there are few of them, they are kind of spread evenly amongst the vertices. And so the question is there a more nuanced way to understand boundary that can capture this intuition? So another very instructive function to look at is the anti-majority function. So here the distance to monotonicity is a half, and the negative influence is square root d because there are d choose d over 2 points on the boundary, each with negative influence d over 2. Right? And so intuitively there are many edge violations which are concentrated on few vertices. And because the negative influence is root d, a random edge will find a violation with probability 1 over root d. Whereas in the anti-dictator function, there are few edge violations which are spread amongst many vertices, and here a random walk will find a violation with probability 1 over root d. So this is the trade-off that we would like to capture. And so one way to do this is to look at this quantity, which is the average square root of the negative influence of a point. And this might seem quite esoteric, but if you think about it, in both of these examples, this quantity is theta of 1. And amazingly, Koopmans and Safra were able to prove that this quantity is always omega of the distance to monotonicity. And using this inequality, they were able to obtain a square root D query tester. And so in summary, there is this very cool phenomena that directed isoperimetric inequalities are the key to analyzing monotonicity testing algorithms. And as these inequalities improve, so do the testing results. So as I mentioned in this original paper, they proved a directed version of Poincaré's inequality, which led to the tight analysis of the edge tester. And a version of this inequality was proven also for the hypergrid domain shortly thereafter. Then in 2014, Chakrabarty and Seshadhri were the first to get little o of d, and they did this by proving a directed version of a stronger isoperimetric inequality due to Margulis. I won't be getting into the details of this because it will require more notation, but just know that it's stronger than the directed Poincaré inequality. Then we actually were able to generalize this to all values of n, and this is what allowed us to get little o of d for hypergrids. And in 2015, Koopmans and Safra proved this inequality, which I discussed on the last slide, and it turns out that this is a directed version of an even stronger undirected isoperimetric inequality, which Talleyrand proved in '93. And using this directed theorem, Koopmans and Safra obtained the optimal non-adaptive monotonicity tester, making square root D queries. And in a somewhat recent work, Polyvore, Raskolnikova, and Weingarten were able to remove this log D factor in the denominator. So it was left open whether this inequality can be generalized to all values of n. And this is our main contribution, so we're able to generalize this inequality to all values of n, so to general hypergrids. And this is what we use to obtain our n square root D query tester. Okay, so now in the second half of the talk, I'm going to tell you about this inequality. The first thing we need to do is define an appropriate generalization of negative influence. So what we use is this notion that we call thresholded influence. So first I need to give some terminology. So for a function f, we say that a pair x and y is an I violation if x and y differ only in coordinate I and they violate monotonicity of f. So in other words, x and y lie on the same line in dimension I, and x is below y on that line, and f of x is 1 and f of y is 0. Now the thresholded influence of a function f at a point x, denoted by phi sub f of x, is simply the number of coordinates I for which x is the lower endpoint of some I violation. So for instance, here is a function on 3x3 grid, and in red, let me just highlight the value of the thresholded influence at every point. So for instance, the origin has thresholded influence 2 because it's the lower endpoint of a violation in both coordinates, whereas the top left point has threshold influence 1 because it only takes part in a violation in the first coordinate. And also here we're charging all of the violations to the lower endpoints, meaning that if the function has a value 0 at a point, then it will just have threshold influence 0. All right, so using this notion of influence, we're able to prove the following inequality, which says that the expected square root of the threshold influence is always at least omega of the distance to monotonicity divided by log n. And note that importantly, when n equals 2, the threshold influence coincides with the negative influence. And so this generalizes the inequality that Koopmans or Safra proved to any value of n. And in this parallel work that I mentioned from ITCS this year, Braverman, Koht, Kindler, and Minzer proved the same inequality using the same notion of thresholded influence, but with the loss of poly n in the denominator on the right-hand side instead of log n. Okay, so before talking a little bit about the proof ideas, I have to tell you a little bit about this concept of robustness, as it turns out to be quite important for analyzing monotonicity testers. So if you recall, in my definition of threshold influence, which I gave a couple slides ago, I was charging all of the violations to the lower endpoints, right? And this might seem somewhat arbitrary, and in fact, in order to analyze the monotonicity testers, we have to prove this isoperimetric theorem. We have to prove that it holds regardless of how we charge the edge violations. So this is sort of the concept of robustness, and so now let me define this formally. So let me denote by E the set of all pairs x and y which differ in exactly one coordinate. And now the idea is we're going to use a coloring chi, so a bicoloring on this set of edges, in order to sort of adversarially charge the violations. And then we need to argue that the inequality still holds. Okay. So formally given a function f and a coloring chi, which assigns a value of 0 and 1, or 1, to every edge. So the colorful influence at a point x is now the number of coordinates for which x participates in a violation in that coordinate, where the color of that violation corresponds or equals the value of the function at that point. So in summary, when a pair xy is colored 1, you're charging it to the lower endpoint, and when it's colored 0, you're charging it to the upper endpoint. So it turns out that we're able to prove the following robust version of the inequality I showed you on the last slide, which says that no matter how you choose the coloring chi, the expected square root of the colorful thresholded influence is always still at least omega epsilon over log n. And this is also the case for Koopmans and Safra. They're also able to prove this robust version for n equals 2, and in fact they were the ones who introduced this concept. And I'll just mention that robustness makes the proofs a lot more challenging. So using this inequality, we're finally able to analyze our tester, which makes n square root d queries. And I'll just mention that the optimal dependence on d is really coming from this robust isoperimetric inequality. And the suboptimal dependence on n is coming from the fact that the underlying graph that we're testing on has degree n in each dimension. So when our tester performs its random walk, it picks a step size out of 1 through n in each coordinate. And essentially, there is a particular step size that is going to work, and there's n possible choices. So this is where we get our loss of n. So now in the remainder of the talk, I'm going to give you just some of the high-level proof ideas, but focusing on the non-robust version. So at the core of our proof is something called the sort operator, which is defined as follows. So for a function f and a set of coordinates s in 1 through d, we denote by s circ f the function obtained by sorting f on each of the coordinates in s in increasing order. So for instance, here is a function on the two-dimensional cube, and applying the sort operator with respect to the empty set does nothing. And applying the sort operator with respect to the first coordinate sorts the values of the function along that coordinate. So for instance, along the lower edge, the values swap. Applying the sort operator along the second coordinate does the same thing, but along the vertical dimension. And now applying the sort operator on both coordinates, we first sort according to the first coordinate, and then we sort according to the second coordinate. And now using this operator, we define something that we call the tracker functions. So now every point x in n to the d gets an associated tracker function g sub x, which is a function over the hypercube, where the points in this cube are indexed by sets of coordinates. Right? So formally, the tracker function of x at the point s is defined as the value of the function at x after sorting the function on the coordinates in s. So as an example, here is the tracker function associated with the point 0, 0, the lower left point. And the value of g0, 0 at each point is inherited from the above functions as follows. And now the main inequality that we're able to prove is the following, which is sort of difficult to parse, but we can summarize it as follows. So on the left-hand side, we have the directed boundary of f, and on the right-hand side, we kind of have the average undirected boundary of the gx functions. And now once we have this, we can use the undirected Talleyrand inequality on the hypercube to try to understand the right-hand side. So let me now back up and show you kind of the big picture view of our proof. So as I discussed on the last slide, we proved this inequality, which is kind of at the core and is sort of the main effort of our proof. And it connects the directed boundary, so the expected square root of the threshold influence, to the undirected influence of the tracker functions. And the strategy of the proof is kind of a hybrid argument, which transforms the left-hand side of the inequality into the right-hand side in d steps. And we show that at each step, the hybrid value can only decrease. And this argument is inspired by the split operator, which was introduced by Koopmans and Safra. And it was sort of unclear how this operator would generalize to hypergrids. So conceptually, one of our contributions is that we give a new perspective on this proof that helps generalize the proof more readily to hypergrids. And one of the key tools in our proof comes from the theory of vector majorization. So now one thing I haven't mentioned is that actually we don't know how to prove this inequality in general. We only know how to prove it for a very nice class of functions, which we call semi-sorted functions. And the second ingredient is a reduction to this class of functions. Okay, so what is a semi-sorted function? We define a semi-sorted function to be a function which is monotone in every orthant. So this might seem very nice, but I'll remark that actually all functions on the hypercube are vacuously semi-sorted, right? Because an orthant simply consists of a single point in the hypercube. So already the class of semi-sorted functions is highly non-trivial, right? So if we were to prove Koopmans and Safra's inequality for semi-sorted functions, this would already be a generalization. But as I said, we're able to actually reduce to this case. So we give a reduction from the general case to the semi-sorted case. Okay, so now looking back at the first inequality, we can bound the right-hand side by invoking Talleyrand's inequality from 93, right, for the undirected hypercube. So we can say that the right-hand side is at least c times the average variance of the tracker functions, where c is some constant. So now the final ingredient of our proof is to somehow connect the average variance of the tracker functions back to the distance to monotonicity. And the proof here is quite similar to arguments that were present in Koopmans and Safra's proof, along with the follow-up work by Polavor, Raskadnikova, and Weingarten, who removed the log d factor from their inequality. Okay, so this brings me to my last slide, where I'll quickly summarize. So our main contribution is that we generalize the directed Talleyrand inequality that Koopmans and Safra proved to all values of n, and using this obtain an n square root d query tester, which is the first to be optimal in D for any n greater than 2 alongside this parallel work that I mentioned from ITCS this year. So then the obvious question is, can you remove this dependence on n and get a purely square root d query tester? And in fact, in a very recent follow-up work with myself and the same co-authors, we were able to get a d to the 1/2 plus little o of 1 query tester. And the analysis relies crucially on this inequality which we proved in this paper, along with some new ideas that are needed to get around the dependence on n. So this resolves the non-adaptive Boolean monotonicity testing problem up to a d to the little o of 1 factor for all values of n. So the next question is, can we beat this with adaptive queries? So the current best lower bound for adaptive testers is d to the 1/3 due to Chen, Weingarten, and Xi, And on the upper bound side, there is nothing known better than the non-adaptive square root d query tester. And this is all I wanted to say, so thanks so much for listening.